Today we're talking about polar graphs, polar coordinates. Basically, polar coordinates are another way to express where a point exists on the plane. So when we did rectangular coordinates, also called Cartesian coordinates, we would plot a point by using an x or y coordinate. X would tell us how far to go left and right. Y would tell us how far to go up and down. And so when we do that, we would draw a rectangle. We'd create a rectangle. That's called rectangular coordinates. Polar coordinates are another way to find the same point, but finding it in a different way. Now, just to be clear, we're still going to graph on the xy plane. It's just that now we're not going to be graphing using an x coordinate and a y coordinate. We'll graph using different coordinates, and those coordinates are r and theta. R represents the distance from the origin, so therefore radius, and theta represents the angle with the positive x-axis. And by the way, that theta is the same theta that you used when you have done trigonometry in the past. So let's talk about how to go back and forth. First of all, to go from Cartesian to polar, there are various ways to do it, but we could just graph it. So we could graph, this is the point 0, 1 is up here. Notice that the distance to the origin is 1. And notice that to get there, we have to go the angle that would be 90 degrees, or pi over 2. So we could express this in polar coordinates as, so it's usually r comma theta. So in this case, it would be 1 comma pi over 2. Make sure you do put this in radian mode. Everything we do is in radians, not in degrees. Now, there are a couple, polar coordinates are not unique. So there are other ways to express the same point. It's possible to go around the circle once and then stop. So that would be still radius of 1, but this time it would be 2 pi plus pi over 2. Which would be 5 pi over 2. So that would be another way of expressing the same point. Another alteration is, what if r is negative? Now, it seems a little bit strange to talk about negative radius, but it is possible. What if we go around until we stop down here? So we have an angle of 3 pi over 2. Now, obviously, that's the wrong direction. So a negative radius means, okay, face the angle 3 pi over 2 and then go backwards. So even though I'm down here 3 pi over 2, I'm then going to go, instead of in that direction, I'm going to go in the opposite direction. And so my radius would be -1. All three of these polar coordinates represent the same point with the Cartesian coordinates 0, 1. Here's another example, root 2 over 2, root 2 over 2. So that would be, well, the x and the y have the same coordinates, so it'll be right here. For my radius, I know that my y coordinate is root 2 over 2. I know my x coordinate is root 2 over 2. And so the distance, we could do a squared plus b squared equals c squared. We would find that that radius is actually 1. You could also notice that this coordinate, these are the coordinates of a point on the unit circle. And remember, a unit circle means that the radius is 1. And then certainly the angle formed would be pi over 4, or 45 degrees. So it'd be 1 comma pi over 4. And again, there are other ways to express it. Just to practice that, what if instead of stopping there, the other angle, basically going the opposite direction, the other angle would be 5 pi over 4? But again, because basically when I'm facing 5 pi over 4, I'm facing the wrong direction. Now I want to walk backwards, so my radius would be negative, so -1. Okay, r is how far we go away from the origin, and if r is negative, that means we walk backwards instead. And let's see, 2 radical 3 comma -2. So let's see, that would be positive x and negative y, so down here somewhere. X is 2 radical 3. Y is 2. If we perform the Pythagorean theorem, we would find that the hypotenuse here is 4, so my radius is 4. For my angle, I'm looking for this angle right here. So I'm looking for the angle, let's see, a couple ways to think about this. Now that I know my hypotenuse is 4, I know that the sine of that angle is going to be, well, it's going to be negative 2 over 4, or negative 1/2. And so that angle would be negative pi over 6. So 4 comma negative pi over 6 would be the angle. Basically, we need to remember all of our trigonometry. Obviously, we're doing all the tricky stuff here for these problems. Instead of negative pi over 6, you could also use 11 pi over 6. That would be the same angle. Now, to go the other direction, if I gave you r and theta, and you had to find x and y, there is a bit of a shortcut. Oh, actually, go in both directions here. If I gave you r and theta, x would be r cosine theta, y would be r sine theta. If I gave you x and y like the previous examples, x squared plus y squared equals r squared. We certainly used that on the last two examples. And then tangent theta equals y over x. I could have done that on the last example to find theta, use tangent, but because I knew all three sides, I could use really any of the trig ratios that I wanted. But notice that when I use sine, I used the radius, I used the hypotenuse. If all you want to use are x's and y's, it would be tangent. Tan theta equals y over x. So for example, let's find the polar coordinates. The polar coordinates of a point are given. We want to find the Cartesian coordinates. So I know that x equals r cosine theta, so that would be 2 cosine pi. Y is equal to r sine theta, so 2 sine pi. Cosine of pi is negative 1, so x is negative 2. Sine of pi is 0, so y is 0. We get the point negative 2 comma 0. If I give you r and theta, finding x and y is really just about plug into the formulas. Likewise here, radical 3 comma pi over 6. So x equals r cosine theta, so root 3 comma cosine pi over 6. Y is equal to r sine theta. So let's see, cosine of pi over 6 is root 3 over 2. So x is 3/2. Sine of pi over 6 is 1/2. So y is root 3 over 2. And so my Cartesian coordinates are 3/2 comma root 3 over 2. Okay, so this is how we go back and forth between Cartesian coordinates and polar coordinates. We can also talk about going back and forth between Cartesian equations and polar equations. Here we have x squared plus y squared equals 3y. And we're going to basically switch back and forth between the variables by substituting. Now, I could just say, okay, change all the x's to r cosine theta. Change all the y's to r sine theta, and that's fine. And in fact, I'll do that on the right side. 3y becomes 3r sine theta. And I could do that on the left side, or I could notice that x squared plus y squared is r squared. So I can substitute that instead. And now simplifying a little bit, cancel r's on both sides. R equals 3 sine theta. So I've now got an equation for the same curve, but now it's represented in polar coordinates. Now in this case, x cubed y squared plus natural log of y equals 3. I don't see anything nice going on here. Certainly I don't recognize any of the other formulas. So really just all the x's I'm going to replace with r cosine theta. All the y's I'm going to replace with r sine theta. And then the 3 just sticks around. There's really nothing I can do to simplify this, so this is fine. And I mean, if you can simplify like part A, go ahead, definitely do that. But if you can't simplify, listen, this is still a polar equation. It is an equation that no longer has x's and y's, now it has r's and thetas, which is what we've been asked to do. Now, going the other direction is tricky because when we go from Cartesian to polar, if I give you a bunch of x's, worst comes to worst, the x turns into r cosine theta and the y turns into r sine theta. But we don't have, in those equations, we didn't have anything that said r equals or theta equals. So it's definitely more tricky to convert from Cartesian to convert from polar to Cartesian. Basically what we need to do here is alter the equation as much as we can to make it look like the formulas that we have been given. Now, I don't have a formula for r, I don't have a formula for cosine theta, but I could multiply both sides by r. I know that r squared is x squared plus y squared. And I know that r cosine theta is x. So as the problem was written, there was nothing I could do. But once I multiplied both sides by r, now I've made it so that both sides look like a formula that I know. Likewise for this one, sine theta equals r squared cosine theta. There are different ways to go about this problem, certainly. Different things you could consider. One thought that crosses my mind is, what if I divided the cosine theta to the other side? So I get, basically, divide both sides by cosine theta, so that I get tan theta equals r squared. Well, from those formulas, I know tan theta is y over x, and I know that r squared is x squared plus y squared. So that gives me an equation in Cartesian coordinates, or rectangular coordinates. Great. Again, I guess I can multiply everything by x to get rid of the fraction, but there's not a whole lot of point. It doesn't really do much. So the next thing we need to talk about is how to graph polar equations. So let's consider graphing this. Sketch the graph, sketch the polar equation, r equals 2 cosine of 5 theta. Now, there are lots of ways to graph. Maybe you want to, maybe there's some ways that you've got memorized or whatever. I never really memorized all the roses and the Lehmann-Scons. I don't think I've even learned how to pronounce that word. I don't even know if I'm saying it right. And the cardioids, those are always fun. They look like little hearts. I never really memorized that. The way I do it is I figure it out. I make a t-chart for theta, and then, of course, r is equal to 2 cosine of 5 theta. This is how I figure out what the graph looks like. Now, I want my 4 cardinal angles. That's probably not the right word, but I want my 4 main angles around the circle: 0, pi over 2, pi, and 3 pi over 2. I want to get basically the four points of the compass. But I don't want to just write, I'm not just going to fill in those numbers for theta. I'm not just going to write 0, pi over 2, pi, and so on. That's not what I want. I want the first r to read 2 cosine of 0. I want the next r to read 2 cosine of pi over 2. I want the next r to read 2 cosine of pi. And I want the next r to read 2 cosine of 3 pi over 2. Now, the question that we have to ask is, what value of theta should I pick for each of these? Well, in the first case, if theta is 0, this is the cosine of 5, 2 cosine of 5 times 0, which is 0. Next question is, what value of theta should I pick so that I get pi over 2? Well, let's see. If I let theta equal pi over 10, I would have 2 times the cosine of, so this would be, I'll erase this in a second, but this would be 2 cosine of 5 times pi over 10, which becomes the cosine of pi over 2, so that works. For the next one, as long as the angle is pi over 5, 5 theta becomes 5 times pi over 5, which is just, 5 times, try again. 5 theta becomes, I said that right. 5 theta becomes 5 times pi over 5, which is just pi. And then the next one is, I believe, 3 pi over 10. Okay, and now we can evaluate each of these. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. And cosine of 3 pi over 2 is 0 again. And then let me just do one more. 2 cosine of 2 pi. I would get there when theta is 2 pi over 5. And that would be back at 2. Now, let's graph each of these points. And there are different ways to keep your work organized. Certainly when theta is equal to 0, so let's start by finding the angle that's 0. So that'd be out here. I'll erase this in a second. But it would be going along the x-axis. So we're facing the direction of theta equals 0, and we're going to go out 5 units. So I'm getting my first dot. Now we're going to go from theta equals 0 to theta equals pi over 10. So that'd be sort of like this, ish, kind of. Yeah, I guess so. That's about 1/10 of the top half. And as theta goes from 0 to pi over 10, my radius is going to go down to 0. So when I'm facing at 0, we're out here at 5. As theta gets bigger, my radius is going to get smaller and smaller and smaller until by the time I get to that angle, my radius is down to 0. Now the next angle is pi over 5. So that would be, we're squishing it a little bit here, but that's okay. The pi over 5 would be right here. And I'm going to keep extending this to the other side also. As my angle goes from pi over 10 to pi over 5, in fact, let me label those. My radius is going from 0 out to 5, out to -5. So when theta is pi over 5, I'm going backwards 5 units. I'm going to be, I don't know, back here somewhere. And this curve, and it is a nice smooth curve, it's going to curve out like this. As my angle goes, and here's the extension of pi over 10, as my angle goes from pi over 10 to pi over 5, my radius is going to go out. Doggone it. Okay, here's what we need to do. I just made an observation. My radius is supposed to be 2. You guys are probably yelling at me. And that's okay. I couldn't hear you. The radius is 2. I apologize. We're going out to 2. So I'm just going to pretend that each of these points that I'm drawing is 2 units out, and I'm going to ignore the boxes. I'm going to ignore the squares on here. Okay, so as we go from pi over 10 to pi over 5, my radius is going out to -2, and so it starts at 0 and slowly becomes more negative, means slowly goes further and further backwards, until by the time the angle is pi over 5, we are 2 units backwards. And then my radius is going to go back to 0, so now it's going to curve back around and go back to 0. And by the time my angle is 2 pi over 5, 2/5 of pi, so that would be up here somewhere. By the time my radius is back to 2 pi over 5, my angle is 2 pi over 5, excuse me. My radius is going to be back out to 2. We can keep going if you want. I mean, I'm seeing a little bit of a pattern here. If you want, you can continue your t-chart. So how about, let's see, the next one would be, actually, I think it would be pi over 2, wouldn't it? If I want 2 cosine of 5 pi over 2, the angle would be pi over 2, and the radius would be 0. So by the time the angle comes to pi over 2, my radius is back down to 0. All right, let's keep going here. I'm going to continue the chart over here. And I'm just going to observe that my angles are 0, pi over 10, 2 pi over 10, 3 pi over 10, 4 pi over 10, 5 pi over 10. So the next one's 6 pi over 10. Seven pi over 10, 8 pi over 10, 9 pi over 10, and then 10 pi over 10, which would just be pi. And the radii, I mean, I can already see a pattern. It's 2, 0, negative 2, 0, 2, 0. So it'd be negative 2, 0, 2, 0, and then out to negative 2 again. Okay, so when my angle is 3 pi over 5, so that would be here somewhere. My radius is going out to negative 2. And then my radius is coming back to 0. By the time I'm at 4 pi over 5, so over here somewhere, my radius is, my radius is back out to 2. By the time I'm at 9 pi over 10, we're back down to 0. And then the last little bit is going to close the loop. What we end up with is a flower or a rose. Okay, one of the petals is a little shorter than the others. That's okay. We end up with a rose with 5 leaves, or 5 petals, or what. I don't think there's an official mathematical term for it. Anyway, this is the idea. If you're freaking out about this graph, please don't. It's definitely useful, and certainly next class when we start talking about the areas of polar graphs using integrals, you're going to need to know this, be able to come up with this graph, but it doesn't have to be perfect. It takes some practice, and it also does not show up very often. Certainly on the homework, you're going to be asked to do a bunch of these just to get practice, but I don't want you guys, I suspect, especially doing this as a lesson, there's a little bit of confusion, and that's understandable. That's okay. Do the best you can. And also keep in mind, at least this part of the lesson is something that you saw back in pre-calculus. I'm not saying that, or math analysis, I'm not saying that to mean you should get it and whatever. What I'm saying is your pre-calculus teachers could probably answer your questions on these things if you need them to. So if you want to go talk to Ms. Alfonso or Ms. Stockhopper, you can do that. All right, let's try another graph. Before we do that though, let's take a look at what it would look like on our calculator, just to get a feel for it. So on the calculator, I'm going to, first of all, I'm going to change my mode. Right now, you are in, no, I don't know, degree mode, sorry. Left over from geometry. Right now, I am in function mode, okay, that 4th row down. If I change, by the way, you'll notice PAR stands for parametric. So if you ever need to graph in parametric, it's there. We may have even done that last lesson. And then switching over here, this now is polar. And so if I hit enter, now if I go to y equals, it's going to graph r equals a function of theta. In fact, I've already got this in here from when I've taught this class before. So r equals 2 cosine 5 theta. And so now if I graph it, the graph looks like that. Same thing we got. So that is good. That's excellent. If yours doesn't graph the whole thing, go to Window. Notice that my theta goes from 0 to pi. And you can make it more if you want. It would just take longer to graph it. But make sure that your theta goes from 0 to pi, that it checks all those thetas. If yours only goes from 0 to pi over 2 or something, you're only going to get part of that graph. Okay, now let's try graphing another one. Sketch the graph of the polar equation r equals 3. All right, we're going to be happier about this one because it's going to be a lot less work. We are looking for all the points that are 3 units away from the origin. In other words, we don't care about the direction we go. We just want to be 3 units out, which means we're going to get a circle. Okay, let's try that again. That was a terrible circle. All right, it's a little dented on the bottom, but that's okay. There's our circle. And that's it. I mean, there's nothing else to do here. The radius is 3. We want all the points that are 3 units away through. Let's try one more time. I missed. Better. Okay. We want all the points that were 3 units from the origin. We got them. There's our graph. Now sketch the polar equation theta equals pi over 3. So now we want all the points that are in the direction of pi over 3. The radius can be anything. Okay, we didn't mention r, so we are independent of r. R can be anything. Well, let's figure out where the direction of pi over 3 is. That would be this direction, and r can be anything. So I'm going to just keep going forever in that direction. But let's remember that we also want to consider that r could be negative. Right? We're considering both positive and negative r's. So we could also go backwards. We end up getting a line. Theta equals pi over 3 is a line through the origin with an angle pi over 3. Okay, but again, there's no work to do for that one. We recognize what it's asking us for, and we graph it. Sketch the polar equation r equals secant theta. Okay, well, this one's a little bit trickier unless you try something different. Because we are allowed, if we want to, we are allowed to find the rectangular equation. And if we do, maybe that one's easier to graph. So if I think about it, this is r equals 1 over cosine theta, which means that r cosine theta equals 1, which means, well, x equals 1. Right? We learned that r cosine theta is just x. So really, we're being asked to graph the line x equals 1. There it is. Done. So yeah, trying to graph that leaving in polar would have been really tough, especially since I don't know a whole lot of values of secant theta, and especially since secant theta has asymptotes, or values of theta I can't plug in. Certainly in this case, changing into Cartesian made life a lot simpler. Okay, let's consider this problem. For the polar graph, r equals 3 minus 2 sine theta. We're not being asked to graph this time. This time we're asked to find dy over d theta and dx over d theta. Now, r equals 3 minus 2 sine theta is a graph. dr over d theta would represent, dy over d theta would represent the rate at which the y coordinate is changing as theta gets bigger. I don't know what this graph looks like. Actually, I guess we can graph it. I mean, we've got our calculator, so let's graph it. We certainly don't need to graph it to do this problem, but just to understand what we're talking about, let's graph it. So my equation is 3 minus 2 sine theta. By the way, I forgot to mention this earlier. To find theta, you can press the same button as you normally do to find x in Cartesian coordinates. That button is the button that's just to the right of the alpha button. That button is the variable button, and it'll put in whatever variable would be appropriate to the mode that you're in. So if I graph it, so here's a graph. Actually, I suspect if if I extended my theta to go to 2 pi, I get a little more graph. There we go. So this is that cardioid that we were talking about earlier. Basically, this says that if I were to pick any point on the graph, say this point, is this going to work? Yep, this point. As theta increases, of course, theta always goes this direction. As theta increases, dy over d theta would be the rate at which the y coordinate is changing. In this case, it would be a positive number because y is getting bigger. And dx over d theta would be the rate at which x is changing. If we're going around that way from this point that I've identified, dx over d theta would be negative because as theta gets bigger, x is going backwards. X is going to the left. Well, in order to answer this question, we need to first express y as a function of theta. We need to express x as a function of theta. And so, well, we can actually do that. We know that x equals r cosine theta. And we know that y is equal to r sine theta. But we also know that we're on this graph, which means that r is 3 minus 2 sine theta. And then for x, that's to be multiplied by cosine theta. And for y, that's to be multiplied by sine theta. And I guess you could simplify that, but there's not a whole lot of point. The problem is saying, what is dy over d theta and dx over d theta? That's saying, take the derivative of x, which we've expressed as a function of theta. So in this case, dx over d theta, we need the product rule, so it would be the first times the derivative of the second would be negative sine theta, plus the second times the derivative of the first, which would be negative 2 cosine theta. There's not really a lot we can do to simplify this. I don't think we're going to find that anything combines or anything, so this should be a good final answer. This is dx over d theta. And then, of course, dy over d theta, we would again do the product rule for the y. So again, first, times the derivative of the second, that would be cosine theta, plus the second, times the derivative of the first, which is again negative 2 cosine theta. In this case, it simplifies a little bit, but there's not much point. Okay, and then if it had asked us to find the value of these two derivatives at a point, we would plug in the point. You know, it would give us some value of theta, so we'd plug in the point, and then whatever number we got, that would be the rate at which the x coordinate is changing, and the rate at which the y coordinate is changing. Now, it's interesting to point out something that's going on here. Haven't we basically expressed, let me erase, that's all right. We've basically expressed x as a function of theta. And we've expressed y as a function of theta. Here's why I bring this up. Oh, I'm sorry, I just noticed a mistake. This derivative should have been dy over d theta. I apologize. It's a weird thing about making these videos. When I make a mistake, you guys probably all notice them, and I don't even notice them until later, and then I feel silly. At least when I'm teaching live, you guys are there to point out my mistakes. So, okay, back to my conversation here. We have expressed x as a function of theta. We have expressed y as a function of theta. Think about what I just said. We have expressed x and y in terms of a different variable. You might even say that we've expressed x and y in terms of a parameter. The difference is, instead of the letter t for our parameter, this time we're using the letter x, or excuse me, the letter theta for our parameter. But we have expressed x and y parametrically using the variable theta. And so among other things, we could find, if we wanted to, we could find dy over dx. As we learned last class, dy over dx is equal to dy over d theta, in this case, divided by dx over d theta. I'm not going to rewrite it, but we could then just insert the two equations that we found for dy over d theta and dx over d theta. So, and now let's remember what dy over dx represents. Dy over dx is the slope of the tangent line. So if I go back to my graph here for a second, if I were to find the value of dy over d theta at this point and dx over d theta at this point, at the red point that I've identified, dy over dx would be the slope of the tangent line at that point. Dy over dx will represent the same thing it's always represented, the slope of the tangent line. The difference is this time we're not thinking about f prime of x, it's polar, so it's more involved than that. But we can find dy over dx. Now, there's a formula for this. Here's the formula for finding dy over dx if you're given the polar function r equals f of theta. I don't want you to memorize this. I want you to do this problem like we did the last example. Express x as a function of theta, express y as a function of theta, and then find the derivative of that parametric setup. There's no point in memorizing this. It's just one more thing but it's just based on something we already know how to do. So don't even bother using this formula. But it's here for anybody who wants to use it. So for example, let's find the equation of the tangent line to r equals sine theta when theta equals pi over 6. We know that x is equal to r sine theta. No, we don't. We know x is equal to r cosine theta, sorry. R cosine theta, so that'd be sine theta cosine theta. Y is equal to r sine theta, so sine theta times sine theta, which would be sine squared theta. I could take the derivative, dx over d theta. It would be the first times the derivative of the second plus the second times the derivative of the first. And so this would be cosine squared theta minus sine squared theta. For y, it's a little bit quicker. Dy over d theta would be 2 times sine theta times cosine theta. We're using the chain rule, and that doesn't simplify any. I do want to evaluate both of these at pi over 2, or pi over 6, excuse me. So at pi over 6, cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. So I get 3/4 minus 1/4, which is 2/4, or 1/2. If I evaluate dy over d theta at that same point, I would get 2 times the sine of pi over 6, which is 1/2, times the cosine of pi over 6, which is root 3 over 2. So that simplifies to just root 3 over 2. So dy over dx would be dy over d theta, which is root 3 over 2, divided by dx over d theta, which is 1/2. So the slope of my tangent line is radical 3. there's one more thing that I'm missing, and that is a point. I've got the slope of my line, but I don't have the point that my line passes through. Well, the point is when when theta is pi over 6. Well, when theta equals pi over 6, x is equal to the cosine of pi over 6 times the sine of pi over 6 times the cosine of pi over 6, which is root 3 over 4. And y is equal to sine squared of pi over 6, so it'll be 1/2 squared, which is 1/4. Finally, we've got our point. We can find our line. Y minus y1 equals m times x minus x1. Do not bother trying to simplify this. That's a good answer. That's got the equation of our line. Okay, so today we basically reviewed graphing polar, although it's probably a bit more than just a review. Next, we've also kind of broached the idea of calculus with polar equations. Next class, we're going to talk about integrals with polar and how we can use integrals to find areas of polar curves. Okay, that is the end of the lesson.